In this lesson, we're going to look at determining the derivative with respect to x of the inverse cosh of 5x. And we want to use our implicit derivative approach to determine that. So I'm going to rethink this problem as y equals inverse cosh of 5x, which of course would mean cosh y equals 5x. So what's our next move? Our next move is to take the derivative with respect to x of both sides. The derivative with respect to x of cosh y equals the derivative with respect to x of 5x. We need to know that the derivative of cosh is sinh. So the derivative of cosh of something is sinh of something times the derivative of something, thanks to the chain rule. So the derivative of cosh y is sinh y times the derivative with respect to x of y, which is dy dx, equals the derivative with respect to x of 5x, which of course is just 5. Now our goal here is to find the derivative of inverse cosh 5x, which really means we want to find dy dx. Dy dx would be the derivative of inverse cosh 5x. So if that's the case, we have dy dx is 5 over sinh y. But I need my answer to be in terms of x, not in terms of y. So how do I do that? We have to remind ourselves of our basic identity in hyperbolic trigonometry, which I'll use thetas here just to use a different variable. Cosh squared theta minus sinh squared theta is 1. So what will that give me? Well, I'm going to rewrite this in terms of y's and say cosh squared y minus sinh squared y is 1. And what do I know? I know cosh of y is 5x. So cosh squared y is 5x squared minus sinh squared y is 1. Remember, my goal is to solve for sinh y. So what I have now is I have 25 x squared minus sinh squared y equals 1. So 25x squared minus 1 would equal what? Would equal sinh squared y. So sinh y is plus or minus. I'm going to just choose to focus on the positive version of this. Sinh of y is the square root of 25x squared minus 1. So focusing on the positive version there, what does that give me? That gives me dy dx is 5 over the square root of 25x squared minus 1. And that should be our derivative of the inverse cosh of 5x. So let's examine some of these graphs. Again, our question is looking for the derivative of the inverse cosh of 5x. So going to Desmos, I have the graph of the inverse cosh of 5x. Now take a look at this. Here's the graph of the inverse cosh of 5x. Notice the slopes of the tangent are always positive. So its derivative will never be negative. This function is never decreasing. Now, if we wanted to go ahead and approximate the derivative by brute force, we go with f of x plus h minus f of x over h. With a very, very small h, I'm using an h of 0.001. So this is my computer constructed approximation of the derivative. It looks like this. Notice in the beginning, the derivative of inverse cosh of 5x is very large. And then it gradually gets closer and closer and closer to 0, more and more horizontal. So that's what the derivative of that cosh function looks like. Now, again, recognize my original function here. The slopes of the tangent are always positive, Notice my computer-generated version of the derivative, again, always positive. Also notice my domain here, right? What's my domain? What x values are allowed in inverse cosh of 5x? The only x values that are allowed in inverse cosh of 5x are positive values. So I'm not really allowed to use negative x values. But if I use my formula 5 over the square root of 25x squared minus 1, that would allow negative values. So that's what that function looks like. So the domain is a little bit off. In reality, we are restricting ourselves to positive values of x. And once we do that, if we say indeed that we're only focusing on the positive values of x, now we would have these two functions matching. This is the one that we computed by hand, and this is the one that we did using brute force f of x plus h minus f of x over h to show that those two functions are equal. Okay, well, let's do the same thing for an inverse sinh. Now that we see the process, so we're using an implicit derivative to find the derivative of the inverse sinh of something. So here's our goal. The inverse sinh, we'll fix that. Derivative with respect to x of the inverse sinh of 3x, let's say. So again, how are we going to do this? We're going to rewrite this as y equals inverse sinh of 3x. So sinh of y equals 3x. And we want to find a dy dx. That's our goal with this process. And then we're going to take the derivative with respect to x of both sides. The derivative with respect to x of sinh y is the derivative with respect to x of 3x. So I get cosh y dy dx equals 3, and dy dx equals 3 over cosh y. But again, we're not finished because I need my answer to be in terms of x, not in terms of y. So my fundamental identity, again, for hyperbolic trigonometry, cosh squared y minus sinh squared y equals 1. This time we are saying sinh y is 3x. So sinh squared y is 3x quantity squared. So we get cosh squared y minus 9x squared equals 1. So we get cosh squared y equals 1 plus 9x squared, or if you like, 9x squared plus 1. Taking the square root of both sides, again, we're just going to focus on the positive part. Algebraically, we should say plus or minus, but I'm going to focus on the positive part here and say 9x squared plus 1. So if that's the case, we will say that dy dx should be 3 divided by the square root of 9x squared plus 1. So we believe, what do we believe? We believe the derivative with respect to x of the inverse sinh of 3x is 3 over the square root of 9x squared plus 1. So let's go back to Desmos and let's check that. So instead of inverse cosh, doing inverse sinh here, and we want inverse sinh of 3x. Let's see what that looks like first. We'll turn that one on. Inverse sinh of 3x. Again, let's look at the derivatives. Function is always increasing. Derivative is never negative. Domain here, though, is all real numbers. That's a little bit of a change from what we had before. So that's our inverse sinh of 3x. Now we'll go ahead and do the derivative via brute force, f of x plus h minus f of x over h for a small value of h. And what do we get? We get this. So notice, this is our original function. Where is the slope of the tangent the greatest? Here, it looks like it gets all the way up to 3. Notice here it's virtually horizontal, so the slope is low. It gradually gets more and more vertical, slope increases. it gets to this point, that's the maximum value. Also notice a point of inflection, interestingly. The derivative is the highest, and then it becomes more and more horizontal, and it goes to 0 again. So there is our derivative of inverse sinh. We think it's 3 over 9x squared plus 1. So let's go ahead and look at that. 3 over 9x squared plus 1. And we'll turn this one off and see if it matches. Does it match? Looks like it does. Looks like it does. And again, there's no restrictions on the domain here. So those two functions look the same. So indeed, our implicit derivative approach to finding the derivative of the inverse sinh and the inverse cosh worked effectively.